Okay, so I have a couple of theorem type questions. I think I'll do 3. Okay, so question 11 at the end of chapter 11, sorry, no, 12, on permutations in the text. It asks you, prove that the order of a cycle is equal to its length. The order of a cycle is equal to its length. Alright, so here's a sort of generic cycle, right, of that form, and its length is n, so let that be n, and you have to show that its order, now that's the order of an element, right, and remember the order of an element is the smallest positive integer k, so that a raised to the power k is equal to the unit. That k is the definition of the order of an element, and we're asked to show that, prove that the order of a cycle, so here's your cycle, so we have to show that this k here, if we apply this permutation k times, we will get the unit element. Follow that? Let me sort of state that a different way. How many times do we have to apply this permutation? Because it's this cycle, it's a permutation, right? It's a special kind of permutation. And therefore, as a permutation, it's a member of a group. And which group? Well, this one, of course. S of n, right? Hold on. I better make that a different symbol. S of p, let's say. So p could be larger than n. All right. So anyway, so this cycle is a member of a symmetric group, and therefore, as a member, it will have an order. It's this k, this integer k, smallest k, positive integer, such that the member, where we could call this c, c for cycle. So this would then be c to the power k. Okay. So we have to show that if we apply this k times and get e, that this k is actually n. Right? That's what we have to prove. We have to show that the order of this cycle is equal to its length, right? And the length, by definition, is n. The number of what? Items? The number of elements in your cycle, which is n. All right, let's try and prove that in general. So let's, to start with, let's take all the objects in your set that you're permuting, right, and put them in a row. And each item has some kind of identifier. So let's say it's an integer identifier. So object 1, object 2, well, from your point of view, object 1, object 2, object 3, object n. Okay? So we'll have dot, object 1, object 2, whatever. But I'm only interested in these ones. So I'll put a1, a2, a n minus 1, a to the n, Okay, so I've just put in a row, a long line, all the objects in numerical order according to their ID, their numerical integer ID, and one to whatever, well, p. Right? I guess that's the pth one. The number of objects in your symmetric group. Okay, now apply this to this. Now if you do it once, now here I'll put the count of the number of times you've applied this cycle to this initial line, if you like. Okay, so do it once. So you will get, now what is it? It's a cycle, right? So A1 goes to A2, A2 goes to A3, A to the N goes to A1. So you apply this permutation to your objects, and your A1 will go to A2, your A2 will go to A3, this will go to A to the N, and that will go, A to the N goes to A to the 1. So this goes to A to the 1, right? That's after applying it one time. And look what's happened. I mean, just look visually. You can see that these objects here, if you like, have all have shifted up relative to these positions by one position. And I don't mean that one's gone to that one. I mean this one's gone to that one, right? So this has gone to, this one's gone to there, this one's gone to there, that's gone to there. So they've all, in that sense, they've all shifted up one, right? Okay, so do it once more. So apply this permutation again. So now we've done it twice, and this is the result. So this will now become A3, and this will be A4, and this will be A1, and this will be A2, all right? Okay, now question. You can probably see a pattern, probably see where this proof is going in already. Question. How many steps do I need? Like, how many times do I have to apply this permutation to get my A1 here back to here, back to the original? Well, so I'll just go ... and eventually I'll get back to this. They just keep shifting up one in terms of these positions, until eventually I get back to what I started with, right? Now the question is, how many times? To get that, I had to apply this permutation twice. So the question here is, what is this number? How many times do I have to apply this permutation to, once, twice? So what is this number? Well, how many of these positions are there? Well, there's n of them, right? There's one, there's another, and in total, this is quite generic, quite general. There will be n of these positions. So how many times do I have to apply this? And I'm shifting them up each time, by one. So after two applications, my one here has moved two positions. But there are n positions. So I'm going to need n shifts, if you like, to get my one to go all the way back again. I'll need n shifts. So this will be n. Follow that logic? Right? So it took me n applications of this to get me from this to this. Now what is that to that? Well, it's the same, right? All of these map to the same one. And all these, they all map, whatever it is to whatever it is, the same. You don't care about these. They don't change. It's only these ones that are changing because of the cycle, right? So to go from this to this, what permutation have you used that gives you the same? Well, it's E, right? It's the unit permutation. So in other words, C, this permutation, so C to the N gives you E, right? I have to apply this N times to take me from here until it's eventually the same again. So c to the n equals e. And that implies that n equals k. Right? Because, or if you like, k equals n. Because when k is equal to n, I get the unit element, right? So if k equals n, that means the k here, by definition, is the order of the element, the order of this permutation, and n is the length, right? Therefore, the order of this permutation, it's just a general one, n is quite general, so true for any cycle, sorry. So the order of the cycle, which is k, here, is equal to its length, which is n. K equals n. So, done that, right? Next one. Prove that the order of any permutation is equal to the least common multiple of the lengths of its component disjoint cycles. Okay. Show that the order of any permutation. So here's a permutation. Right? Let's call it P. P for permutation. Show that the order of any permutation is equal to the least common multiple of the lengths of its component disjoint cycles. Well, all right, well, call that C1, okay, C2, C3. Dot. CN, let's say. That's quite general, okay? All right. Now we've just proven that the length of these cycles is equal to for each one, the length of a cycle is equal to